Hi, this is Dr. Franklin. I'm going to be walking through a presentation here of how we covered exploring exponentials with future value problems during our grant class in October. Basically, we wanted to explore the use of exponential functions in a particular application, namely in mathematics of finance. And a very interesting problem comes from the question of, in a more realistic scenario than is typically covered with compound interest, how does your money grow when you contribute into a savings account? In most of our very simple examples that we do, say in our algebra courses, we throw out the compound interest formula. And I got a quick little motivating example here where you invest money up front. Here's an example. Beginning at age 25, one would like to invest a certain amount of money every month so that they can retire and live comfortably off their savings. How much, and the accrued interest, of course, how much should they be putting aside in order to reach a certain savings? All right, so recall that the compound interest formula is based on the initial investment, the P, called principal, which accrues interest and is compounded at irregular intervals. And the final value of the account is given by this formula. P is equal to 1 plus R over N to the NT, where R is the annual interest rate, N represents the number of compounding periods per year, and T is the number of years. And as kind of I guess a shortcut, maybe some simplified notation for what's going to be coming next when we look at future value problems, I like to modify this formula slightly and look at an alternative form of compound interest. Instead of writing in terms of R and N and T, I simply want to write it in terms of whatever the interest rate is for the given compounding period. For example, that R over N happens to be the interest rate for a given compounded period. If, for example, I was R over N, if the annual interest rate was R and N was 1, so you did it once a year, then I and R are the same thing. But if you do it twice a year, if you do it 4 times a year, all you have to do is divide your annual interest rate by the number of times a year that you do the compounding, and you'll get whatever the interest rate is for that compounding period. And then instead of putting NT up in the exponent, where it is the number of compounding periods time per year times the number of years, we could just put up there, what's the total number of compounding periods that we actually cover? And I adjusted my notation slightly whenever we were presenting this in class. So instead of putting a little M, I'm going to put N, right? So where R is the annual interest rate and M is the number of compounding periods per year. And then we're going to use capital N over here to represent the number of compounding periods total. Okay? So whenever I say N times T, that's going to be the total number of compounding periods overall. So let's use that formula and see what we end up with. How much should new parents invest now, for example, in an 8% compounded semi-annually account to have $80,000 towards their child's college education in 17 years? Well, we start by looking at the interest rate. Since it's compounded semi-annually, you're going to take the 8% interest rate here, and semi-annually tells us it's going to happen twice a year, so take that and divide it by 2, which is going to give us 4%, or as we plug into the formula, that's going to be 0.04. All right, and now, what is the total number of times that this is going to be compounded? Well, if you've got twice a year, and it's for 17 years, 2 times 17 is going to give us 34, and then our principal, sorry, not our principal, we don't know what our principal is, we need to find out what our final amount is going to be. That's actually given to us, 80,000. So if we plug that all into the formula that's up above, up here, right, then you're going to say, okay, 80,000 equals whatever the principal is times 1 plus I is 0.04, raised to the capital N, which is 34. All right, so that leaves us with P equals, take the 1.04 to the 34th and divide it across, take this right here, and divide it across to the other side over here where the 80,000 is. And you'll end up with 80,000 over 1.04 to the 34th. Plug that into your calculator and it shows you that you need to invest up front $21,084.17 in order to have $80,000 towards your child's education in 17 years. While that's the correct answer and mathematically sound, the problem is, or at least one of the problems is, that you're not going to have, in most circumstances, unless you have a windfall or a massive inheritance show up all at once, $21,084.17 when your child is just born to begin saving. What is a much more likely scenario? That you are going to set aside so much money each month, or maybe each 6 months, every year, as you accumulate more income. You can set aside possibly more, but at the very least, you're not going to put it all up front. You're going to set aside a certain amount of money each compounding period, or each periodic set of time, and that's going to accrue interest. So the question becomes, how do we calculate that value in an interest-bearing account? So let's start with some terminology, shall we? Annuities. So an annuity is any sequence of equal periodic payments. So we're making the same sized payment at regular intervals. If the payments are made at the end of each time interval, then the annuity is called an ordinary annuity. That means it doesn't have any time to accrue interest during that compounding period. So that makes a difference in how this is calculated. You'll see some examples in your homework where you adjust whether or not the payment is made at the beginning or at the end. If it's made at the end, that's what we call an ordinary annuity. So what is the future value of an annuity if we use what we already know? So suppose we decide to put $100 into an account every 6 months, and this account is compounded semi-annually at an annual rate of 6%. All right, so what we're going to look at is what happens to each one of those $100 over the length of the investment. So if we put $100 into this box, that's at the end of the first half year, the first 6 months, that $100 is going to accrue interest over the next 6 compounding periods, right? From 1 to 2, from 2 to 3, 3 to 4, 4 to 5, 5 to 6. That's actually 5 intervals. It's going to have time to accrue interest. The second $100 is not going to have the same length of time to accrue interest, and so on all the way down each $100. So look at the last $100 first. That's actually the easiest one to consider. It is at the very end of the entire investment, which means it has had no time to accrue interest. Its final value is exactly $100. Now let's look at the second $100, second from the bottom. It has one interval over which it can accrue. Now the interval is a half year. If the annual rate was 6%, then the interest rate for the half year, the semi-annual period, is going to be 3%, right? 6% is divided by 2. And so over one of those compounding periods, you're going to gain 3%. In other words, 100 times 1.03. The $100 that's third from the bottom is going to actually have 2 of those intervals over which it can accrue. So you end up with 100 times 1.03 squared. The one above that is going to be 100 times 1.03 to the third, because it has 3 intervals over which it can accrue interest. Notice this is just these formulas that I have here down the side are just the compound interest formula for an initial investment of $100 over 3 periods. This one would be over 2 periods, this one's over 1 period, this one's over no period. So it's still just the compound interest formula, but each $100 is accruing a separate amount of interest. The one above that would be 100 times 1.03 to the 4, and of course the one above that is 100 times 1.03 raised to the 5th power. Now the final value of the account is going to be this entire column added up. So let's write that out and see what we have. If we take the top, and I'm not going to flip back to the slide, but all I'm doing is I'm adding up the columns of what you saw up above there. You took 100 times 1.03 to the 5th, plus 100 times 1.03 to the 4th, plus 100 times 1.03 to the 3rd, and so on all the way till we get to the 100, which was the bottom box. And I can plug all of that into my calculator and get a quick answer of $646.84. Now, you can see already there's going to be a small problem with this, is that this formula is ever expanding the longer you have the investment in the account. We can use a little bit of algebra and some understanding of exponential functions to actually come up with a trick to come up with the formula for the future value of any account that doesn't require an ever-expanding formula. All right, so let's think about this in general terms. Let's say we've got n compounding periods. Let's say we're going to put the same amount of payments in all of these boxes here, and let's say that our interest rate is going to be I. All right, so I'm going to put the payment all the way down. Actually, let's do I, capital N. If we start with this payment right here, it's going to accrue over n minus 1 intervals, so it's going to end up being the payment times 1 plus I to the n minus 1. Notice it's not n intervals because we didn't do it until the end of the first one, and so if you count the number of intervals here, it's one less. You can go back and look at the previous one. You saw that we did 6 here, but the final power up here was a 5. And if you do that all the way down, you're going to have 1 plus I to the n minus 2. Payment is times 1 plus I to the n minus 3. Put payment in all of these boxes. You're going to have payment down here times 1 plus I just to the first, and then the last payment doesn't accrue any interest. Let's add up now this column, every one of these boxes, to get our future value. So this is what our formula up above looked like up here, only now with general variables like payment, I, and capital N. And so that's what we end up with right there. The hard part about this formula, or at least the discouraging part about this formula, is right here. It is the ... right? The ... means that if, for example, I did this on a monthly basis for 20 years, I would have to do 20 times 12, 240 terms added up here, which would be a pain in the tuchus. So we're not going to do that. I'm going to show you that there's an actual little trick here. Comes from our understanding of something called geometric series that we cover in algebra, but you may or may not have seen it. It's not a big deal if you haven't. Let me just show you a few little steps here that's going to let us figure out a way to get this formula down into something much, much simpler. So here's the trick to answer the question of how do we write this without the ... that is, we want to find it in closed form. What you can do is take that future value equation we just wrote at the top of the other page, or at the bottom of the other page, and multiply both sides by 1 plus I. Now, how does that help? Well, watch. We're going to multiply by I, we're going to subtract from that other equation, and you're going to see what ends up happening. So I'm just going to rewrite the future value equation, except I'm going to multiply both sides by 1 plus I. Okay? So the left-hand side had future value, or FV, so I multiplied it times 1 plus I. On the right-hand side, every single term had a 1 plus I in it, so I'm just raising the exponent power by 1 in every term. Payment times 1 plus I to the nth, plus payment times 1 plus I to the n minus 1, plus payment times 1 plus I to the n minus 2, and so on. And the last term has a 1 plus I in it, when before it didn't have anything. Okay? Now, the original equation just looked like this. It was FV, and it was payment 1 plus I to the n minus 1, payment times 1 plus I to the n minus 2, 1 plus I to the n minus 3, all the way down to payment times 1 plus I plus payment. Now, all I did, you see I left a space right here, and the reason I did that is so that my terms lined up, but all this is that's written right here is exactly the same formula for the future value that we came up by adding up our boxes on the previous slide. Now, what I'm going to do is step 2, I'm going to subtract these two equations. I just subtract the original equation from the result that we got when we multiplied by 1 plus I. On the left-hand side, if you subtract, you're going to have 1 plus I times FV minus FV. That's the left-hand side, the two equations. On the right-hand side, when you subtract, you are going to have to change the sign of every term in the second equation because you're subtracting it. That's going to be a minus all the way across. And then when you do that, notice what happens to the second term, that is the PMT times 1 plus I to the n minus 1. They're subtracting the same. Those two things are going to cancel out. And in fact, the next terms are going to cancel out, and everything's going to cancel out all the way down to here. Right? But you're still going to be left with this last payment down here, so all you've got is this first one here minus this last one here. We've managed to subtract out every single term. The dot, dot, dot disappears. So it looks like this. Notice now what we have here, while it's not solved for FV just yet, it is a formula based on our previous formula. Therefore it's true, but it's not ever expanding. Right? There's no dot, dot, dot here. There's no dot, dot, dot here. And in fact, notice on the left-hand side, if you multiply out this FV times 1 plus I, you get FV plus IFV. And then you've got a minus FV, and those two FVs here are going to cancel. So you're left with IFV is equal to the payment times 1 plus I to the n minus 1. Now where did I get that? I just took the payment out of both of these and put it out front. Now take this I right here and divide it across, and you have what's called the future value formula. You will know from this formula what the final value of your account is if you do periodic payments of equal size into a interest-bearing account, a compounding interest account, just by using this formula right here. So let's write it formally into our formula box up here. The future value formula says that the future value of an annuity is payment times the fraction 1 plus I to the n minus 1 all over I, where I is the interest rate per period and n is the number of compounding periods. So let's do just some examples here of using this particular formula to see what kind of results we end up with. In fact, I'm going to do one walk through the step-by-step of it, and then for the rest of these we did them quickly in class just by plugging them into our calculator. So I'm not going to write out the formula, I'm just going to write down the answers, but give you some of an intuition about how fast these things can grow even with regular small-sized payments. Now let's start with one where Marcus is going to be investing $2,000 each year into an into a retirement account that has an APR, an annual percentage rate of 7.5% compounded annually. The question is, how much money will there be in Marcus's retirement account when he retires at age 65? So let's figure out what we know. We've got to find the future value. So if we look at this formula up here above, we first need to know the payment. Clearly that's going to be the $2,000. And I say at the beginning of each year, actually what I meant was end. Sorry about that. The interest rate, because we haven't talked about what to do about the beginning of the year. In fact, that's something for you to discover on your own as you're doing your homework. At the end of each year, he's going to put in $2,000. The interest rate is given to us as 7.5% or 0.075. The number of compounding periods is going to be how many years, because this is annually contributed. It's annually compounded. So there are going to be from 25 until he retires at 65. That's 65 minus 25, or 40 years. So let's plug all that in. Future value is going to equal 2,000 times 1 plus 0.075, or 1.075 to the 40th, right, from here, minus 1 all over 0.075. So throw that all into our calculator, and our final result is we end up with $454,000, 513 and 4 cents. $454,513.04. So is that a lot? I mean, it's obviously a sizable amount, but just think about how much did we actually contribute? How much did Marcus put into that account? Well, if he contributed $2,000 a year for 40 years, all you got to do is multiply 2,000 times those 40 payments. Of that $454,513, only $80,000 was principal. That's how much money he put into it. The rest was interest. Now, how much of a difference would it make? Oh, by the way, let's go ahead and answer this final question. Sorry about that. What is the amount that was interest? It's the difference of those two. $374,513.04 was interest. Now, the next question that I asked was how much difference would it make if instead of 7.5% we had 6%, or if we had 11% interest rate. So all you got to do is change that in the future value. If we plug in 0.06 instead of 0.075, notice the result turns out to be $309,523.93, or a difference of, from the 454 above, it's $144,989.11 less when we lost 1.5 in percentage rate. However, if we go up 3.5 points to 11%, Turns out that the future value is $1,163,652.13, which means an increase of $709,000 plus change. So notice how big of an impact that the percentage rate has on the size of the final investment of the future value. What if instead of investing $2,000 every year, we invested only $1,000? That is, contribute half of what we ended up with. What you'll notice is exactly what you should expect from the formula. Since the payment is this variable that's out front, and that's the only place it shows up, if you double the payment, you will double the investment. If you raise it by 50%, you're going to raise your final investment by 50%. That's exactly what happens when you plug that in. Cutting it in half cuts the final value in half. Raising it by half, from 2,000 to 3,000, raises your final investment by half. And what if, instead of contributing $2,000 at the end of every year, we had an account that was compounded quarterly, and we made our $2,000 payment distributed out over the 4 quarters of the year. So instead of $2,000 the entire year, we made an investment of $500 each quarter, and the account we were placing it into also compounded at the end of each one of those quarters. What difference would that make? Would our money accrue faster or slower, since we're putting in smaller payments, but we're still putting in the same amount per year? Now, your intuition may or may not tell you this, but what it should tell you is that you're going to get more because you're getting money in earlier that begins to accrue interest, whereas the $2,000 had to wait till the end of the year and didn't start accruing till the next year. If you put in $500 at the end of the first quarter, it's got 3 quarters to accrue interest, and so you're going to see growth. But how much difference does it make? All right, well, instead of having 40 compounding periods now, since it was 40 years, we're going to do this 4 times a year. So 40 times 4 gives me 160. 160 compounding periods. Our interest rate is not going to be 7.5%, but it's going to be 1/4 of that because it's the interest rate per compounding period, so it's 0.01875. Our payment now is $500, so the future value, plugging everything in, would look like this. 500 times the quantity 1.01875 to the 60th minus 1 over 0.01875. Dun, 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 drum roll please. What you end up with is $494,273.74. How much difference did it make? The answer is it makes about a $50,000 difference over the life of the investment in this particular circumstance. All right, so I've already done the question at the top of this slide, and I'm going to skip over this one because we ran out of time in class and I skipped over it there, so we're not going to do this particular example, but let's move on to the next one. All right, so let's consider the scenario where you have began investing in annuity at the age of 25 at $400 per month, and it's compounded monthly at a rate of 6%. Your plan is to retire at an age of 65, but due to circumstances beyond your control, after 7 years you cease contributing to the annuity, but it continues to accrue interest until you reach your retirement age. Now, a colleague of yours who just happens to be the same age puts off retirement for 7 years, and then when you both reach the age of 32, he begins investing and you stop, right, and allow your money to continue to accrue. So at that time, your friend begins investing $400 per month in an account that will accrue the same annual rate, and your friend is able to continue saving monthly all the way until his retirement at the age of 65, whose account will be worth more at 65. Now, I'll confess, I made a mistake in designing this problem, and what your intuition tells you to be true actually turns out to be true in this case. At the end, I'm going to ask you to go in and change this 7 to 10. That is, wait 10 years instead of 7, and it'll surprise you that the friend's account won't actually catch it. In this case, let's at least work the problem and see what happens. It happens exactly as you'd expect it to happen. As long as these continue to contribute, he wins. But it's the 10 years that makes a difference over the 7 years. So that's kind of an interesting second problem for you to follow up with. All right, moving to this example. What is the future value? I'm going to break my part of this problem up, the initial part of this problem, into two parts. That is the first 7 years, which is a future value problem, and then after the end of that 7 years, that money is now just going to start accruing interest at a fixed point, and it's not going to be contributed to anymore. So after 7 years, it becomes just a regular compound interest problem. All right, so the future value after 7 years can be found by finding the interest rate for monthly. If it's 0.06 divided by 12, that's 0.005. So I'm going to do $400, and I'm going to do for 84 contributions, that's 7 times 12, 7 years times 12 times a year. So I get 1.005 to the 84 minus 1 over 0.005. Okay. Plug all that in. At the end of 7 years, I have $41,629.57. Now, this amount right here is now like putting the money in the bank and letting it accrue interest for the next however long, right? From the time I'm 32 until I'm 65. So, part 2 of this is for the next 33 years. That $41,629 is just going to go into a compound interest problem, which is 1.005. Now, where did I get the 396? Well, 33 times 12 is 396. 33 years, 12 times a year. Right, that's how many times it's compounding. Notice, I'm not putting $400 in anymore. This just stopped. And now this amount of money is going to accrue interest at this rate, and you end up with $300,028.42. Now, for this last 32 years, now we're going to consider what happened to my friend. The colleague put $400 in there 396 times, and it accrued interest over that entire period and ended up with $496,576.88. Now, just for kicks, and I'm not going to do it in the video, I'll let you do it on your own, change this to 10. And change this to 8%, and you'll see that these actually flip, and that there are situations where stopping an investment and just letting it accrue, and then somebody else starting when you stopped and still contributing for the rest of their life won't catch up with you by the time of retirement. So it's kind of an interesting problem that helps you to realize earlier is better. Don't wait too long to start an investment like a retirement account, because the sooner you start it, the longer it has to accrue interest. All right, and that's our future value sections. I'm going to stop there, and you guys can go tackle some of the work problems that are in the homework.